Cool. Awesome.
Does anybody have homework questions today?
Okay. Yeah, I don't really see them. I do have my purse though. But they're all safety stores too. So no, I don't.
Just a reminder that study group meets tonight. So if you're interested in study group, make sure you attend. Otherwise, it will end if nobody goes to study group. Right now we're in section 4.2. In the next section, 4.3, you need a few things. Compass, which I thought we were using for the Pythagorean proofs, but then we didn't need to. So you'll need a compass, graph paper, and this time a ruler, not just a straight edge. So that will be Wednesday and possibly Friday as well, depending on how things go. How fast we move. I never know how fast we're going to go, how many questions you're going to have. After we do section 4.4, then we come to section 4.5, which is the Platonic solids. The lesson in that section is making the Platonic solids. That's how you learn about the Platonic solids, is to make them. So these are shapes that have fascinated mathematicians for hundreds of years. I'll show you some figures of those. You can find this on Canvas. On the Canvas homepage, there's a module for class activity materials under the module of class activities. So the Platonic solids directions are the directions that Wiley Plus provides. It's in a book with some other materials, so here's the one we're interested in. These are the 5 Platonic solids that you'll need to make. And as I said, making the Platonic solids is learning the section. That's how you learn about them. So when you make them, they should all have, each one should have the same sides. So this one has all triangle sides, and the triangles have all the same length edges. This one is made up of squares, and the squares have all the same length edges as well. This one is triangles. This one is pentagons. This one is triangles again. So each of these figures is all made out of one shape. All pentagons, all triangles, or all squares. So as you make those, you can purchase a kit from the bookstore that has straws and chenille sticks, which are the same as pipe cleaners. That's about $4. So you can get a bunch of pipe cleaners, and then you'd cut them up into lengths, a couple inches long. Don't use your good scissors, because that's probably not good to cut through metal with your scissors you use just for fabric. And you're going to put these shapes together then out of the straws and pipe cleaners. So here's my tetrahedron. Straws come in different thicknesses. So these straws, it worked pretty good to just crimp the chenille stick to help give it a little thickness in there. Some of these shapes that get more complicated, you'll be putting two chenille sticks in. And some of these straws are smaller. So this straw is a particularly small straw. So I don't think I could fit 2 chenille sticks in here unless I trimmed one down. So that's what I did here. I took a scissor and cut the fuzziness off. I did that on 2 ends. And then I can fit more than 1 chenille stick in, so that when it gets complicated and I'm sticking parts together, they can still stick some more chenille sticks in there. So you'll have to experiment with yours and see, do you need to make zigzags out of your chenille sticks, or do you need to make them thinner by cutting off some of the fuzziness? Your sticks should all get cut the same length though, so take a ruler and decide how you're going to cut them. Maybe you cut them into thirds. Whatever you decide to cut them all the same. Otherwise, you're going to have very lopsided shapes. So So I think this one I made 5 centimeter long sticks. And if you don't have a ruler for this part, cut one and then use that as the template for the rest, right? Okay, so you get them all the same size. Does anybody have any questions on constructing these? So these are important. They're how you learn to do the platonic solids is by making the platonic solids. That's how you learn about them. So these are worth 2 class activities because they take quite a while to make. About 2 hours. Some students said an hour and a half. And depending on your personality, you might like it or not. A lot of students actually enjoyed making these. I think if you know that you're going to have to take 2 hours, it helps a little bit, so you're not like the night before trying to make them at midnight. So these will be after spring break. I'm not sure how long classes are going to take us, but I'm thinking about Wednesday. For sure I'll know the day before we need them, so if we need them the Monday right after break, then I'll let you know on Friday, okay? Well, let's go back to where we were working. We were working on the art gallery theorem in section 4.2. So we had looked at particular art gallery layouts, and we're going to restrict ourselves to a particular art gallery. Remember, we were looking at how many guards are necessary to guard an art gallery, and of course it depends on the layout. So we're going to restrict ourselves to a particular layout called a polygonal closed curve. Okay, so this is 4.2 continued. And I kept my notes from 4.2 because we need those drawings up above. So we're looking for polygonal closed curve art galleries. So the description of a polygonal closed curve is a figure made up of straight line pieces We're going to have a figure made up of straight line pieces that are connected end to end. That are connected end to end to form a loop. That are connected end to end to form a loop. So we need to take straight line pieces and connect them one end to another until they close up again. So I'll label the shapes that we made, and you can pick out which one of those is a polygonal closed curve. Okay, which one is made up of straight line pieces, or we'd call those straight line segments, connected end to end until they closed up again? A, B, C, or D? Yeah. C, good. Yeah. So this one, A, is not because it hasn't opening yet. B is not because the square in the middle is not connected end to end to the square on the outside. C is the one that's the polygonal closed curve. D is not because it has these line pieces that are not connected end to end. They're just have one end connected. Our first shape that we looked at was a polygonal closed curve, and we found that we had a security guard at A and B that were not sufficient to see inside the whole compound, at least not the way they were laid out. I don't think we could do this one with just 2 security guards. I think we need one more up here to see in here, or maybe put another security guard here with this security guard. If we put the third security guard in the corner here, would they be able to see up into the peak up there? No, they still couldn't see inside up there, could they? So I'd like you to each make a polygonal closed curve, and I'm going to ask you to trade it with someone, and they're going to find how many security guards they need. Use a straight edge, please. Okay, use a straight edge because otherwise it's going to be hard for the person you give it to decide how many security guards are necessary. So after you make a polygonal closed curve, then I'll ask you to trade with someone. Before you do that, let's count the vertices first. Count the vertices. So the vertices are the corners. For example, this polygonal closed curve C has, let's see, I'll start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 vertices. Okay, so I'll ask you to count the vertices, then trade it, and then with the one that you get, position the least number of security guards that you need to see inside the entire polygonal closed curve. So use your ruler to make sure you're seeing straight. For example, on this one that I have, if I put a security guard in the corner where I put that little dot, that security guard would see through here to there, but then the walls would block part of the view. So the security guard here, I'd need more than one security guard if I put a security guard there. But maybe there's a better placement. Maybe if I put a security guard here, the security guard would see better, because then they could see down this row, this kind of wing and this wing. The security guards can see 360 degrees, but they can't see through walls, and they have to be placed on a corner. So find the least number of security guards needed. So go ahead and start out by making a polygonal closed curve. Don't make it too complicated or your person is going to hate you the rest of the semester, all right? Okay, and I'll come around and see how you're doing, and I'm going to get a count of the number of security guards that we need too. So if you're ready to trade, you can go ahead and trade. If you're working at home alone, you'll have to do this alone, I think.
Okay.
Okay, if you're stuck, raise your hand. Yeah, looks like there's a Did you
I'm too.
Okay. Did you trade with anyone?
Hell yeah. I'm so here.
This one has a little opening and it's kind of hard here. So this one we're working.
Yes.
If you're done, raise your hand too, because I want to record your work at my desk.
Surprisingly, you only need 2 cards. You only did this. She did. Good job. And you got 7. Yeah, I did it right. I need 3 cards though. I do have that extra little spot. Cool. They're going. I didn't write. I'll let you do the writing, but
Are you
So
done?
this is mine, and she did mine, and I did hers.
Okay.
So she had 7 vertices, and then she determined I have 7 vertices, 3 guys. Yes.
There's, I think we can get this one down. Where did you put it down?
Here, another one, and I said like it was a problem.
Because this guy can't see this corner.
No.
Neither can that one.
You're right, the way you have them placed, you're right. But how about if we move one of these, move these two and put one here? Then they can see behind them on both sides because they can see. Here, you think about that. If you can get the number of guards down.
Because they can see everywhere.
We need the least number of guards. Alright.
We want to save money, apparently.
One here.
6 for me.
Should talk
And
to
there.
So maybe you need like one.
Get one down there. Get to one.
It's 2.
No, it's not, because this guy can see down here, this guy can see over there, and I can see here.
One here, it can problem.
So,
Yeah, you look in here and then you could. Yeah, so you just
Put one here.
well, I didn't understand any of the last ones, I just wrote them down and
Sure.
So think about putting
You look this way,
where are they,
and this way.
under like the online exam? I did my wire class, which is fine, but I didn't have the picture for this. That's pretty much. I don't have this like snap or anything.
So let's talk about when you
I got the other one right though. That's all these first or 7th. She determined that are we gonna use these like on graph paper?
No, we're gonna have your
Only we studied it usually.
That was the hiccups last
were you able to get that down at all?
Yeah, to one.
To one?
I don't even know.
Wow. Who sent on record yet?
But I don't know if it has. So if it's down in the corner,
Like I've tried to rough draft that.
Sorry. I have to make a shopping list. So I know what to buy when I'm all I know is I want to make enough money so I can cover our insurance this month. And maybe April. I know I already have some money, but I probably don't have enough this month. I was supposed to do 3 days worth of it. I was kind of looking forward to the time myself. It'll be fine.
But if I don't answer, don't call.
I won't call you. I don't need to call you. I don't want to know. I don't need to know. No, I'm good. Hannah's gonna be working over spring break. I'm hoping to hang with all my friends. She's coming back. Jasmine, we're gonna check on Nate. I can't wait to see her because I really miss her. She's not gonna see me all next summer.
Yeah.
So I'm gonna go stay with mom. I wonder how long they're gonna wait before they get married. They haven't even been together for a year yet.
It's 1:30.
They say as you get older that you fall in love quicker. They say as you get older that you fall in love quicker.
You do, because you don't.
And you're more mature. So.
It's 2 in the morning. So I woke up early to say goodbye to Nicole.
Is there anybody at next?
I need to remind myself to pick up cereal. So I have breakfast.
So I went around and saw all of you, and you told me how many vertices you had and how many guards you needed. So there were a couple people that had 7 vertices, and one of those people had just 1 guard to see everything, and one had 2 guards. So that's why some of these have a couple choices. Yeah. Now what we're going to do is we're going to look at the number of vertices, which I'll call V, divided by 3. So 7 divided by 3 is 2.33. 5 divided by 3 is 1.67. 6 divided by 3 is 2. 3 divided by 3 is 1. So I'm just taking the number of vertices and dividing by 3. 8 divided by 3 is 2 2/3, so 2.67. 4 divided by 3 is 1.33. 10 divided by 3 is 3 1/3, 3.33. 12 divided by 3 is 4. So I made this chart up because I wanted to see if you could notice anything. Does anybody notice anything about the number of guards necessary, the smallest number of guards necessary, and the number of V divided by 3? What can we say about those 2 columns?
Equal or similar.
Yeah, so this column, the smallest number of guards is equal or smaller. Good. Equal or smaller than V divided by 3. And that is what the art gallery theorem tells us, actually. It tells us that if you have a polygonal closed curve with a V number of vertices, and you take that V and divide by 3, that's the least number of guards you're going to be. In fact, it's even more precise. It says if there's a little decimal like this, you can cross the decimal off. Okay? I mean, that makes sense, right? Who has 1/3 or 2/3 of a guard? So here the most we'd need is 2. The most we'd need is 1. And so on. Let's actually go ahead and write the art gallery theorem out. It's kind of long. So get ready to write. Okay. So the art gallery theorem. The art gallery theorem says, suppose we have a polygonal closed curve. Suppose we have a polygonal closed curve in the plane with V vertices. Remember, vertices are just corners. Okay, so suppose we have a polygonal closed curve in the plane with V vertices. Then there are V divided by 3 vertices. There are V divided by 3 vertices from which it is possible from which it is possible to view every point on the interior of the curve. On the interior of the curve. If v divided by 3 is not an integer, if v divided by 3 is not an integer, then the largest number of vertices we need is the biggest integer less than v divided by 3. The biggest integer less than v divided by 3. So let's see what the art gallery theorem is saying. Let's look at it a little more closely. First of all, we have a polygonal closed curve. So on your quiz, you'll have to make sure you're able to pick out a polygonal closed curve. So it's just, I saw lots of them today in class. That was great to see. Here's a selection, actually. These are just line segments connected end to end. Okay? Line segments connected end to end. And I'll be handing this out in a minute. So you have a polygonal closed curve in the plane. That just means this is not three-dimensional, which it would be interesting to expand this to a three-dimensional theorem and see what we could work out. But anyway, this is not 3 dimensions. It's 2 dimensions. It's in the plane. Okay, then there are v divided by 3. You take the number of vertices and divide by 3. And that's the most number of security guards you'll need, because you can see every point on the interior from that. And if the v divided by 3 is not an integer, okay, like we have these little decimal places, so they weren't integers, you can just cross those off. Okay, so you'll need at most 2, not 2.3. You'll need at most 2, not 2 2/3. Well, we always ask in this class and in math, why? Why is it only v divided by 3? How come? Okay. So we'll start small. Start small. Start with a simple one, a simple polygonal closed curve. Now, we can't make a polygonal closed curve with 1 because we can't make a loop. Can't make a polygonal closed curve with 2 sides because that doesn't have any empty space either. We'll start with 3 sides, 3 vertices. So I'll make several triangles that have 3 vertices, one with all angles less than 90 degrees, one with a right angle, and one with an angle greater than 90 degrees. If you use a straight edge, these would look better. Now look at all of these triangles. The art gallery theorem says I need 3 divided by 3 or 1 guard. One guard for each of these triangles to see the whole interior of the triangle. Now, you've looked at several shapes well, I saw several shapes today where it mattered where the guard was placed. For example, the shape that we started this section out with had these projecting triangles, and if you put a guard up here at the point where the C is, that guard can see the whole point, but that's about it. Whereas if you put a guard at the corner, in the interior corner, then the guard could see up into that peak and out around the rest of the gallery. Does it matter on these shapes where the guard stands? No. God, I see head shaking. No, it doesn't matter on any of these shaped triangles. Wherever I put the guard, I'll use a red pen for the guard. If I put the guard here, the guard can see all along the line of sight there. Okay. Even if I put him on the acute angle, when there's this big angle, the guard can still see all the parts of the triangle. Okay, so with three vertices, it does not matter what corner the guard stands on. The guard can see the whole triangle. So it doesn't matter where the guard stands when you have three vertices. The guard can see the whole triangle. Well, let's go on. We'll make it a little bigger at a time here. So how about 4 vertices? So let's draw a couple of shapes with 4 vertices. Well, there's a square or a rectangle. That's pretty straightforward. But what if it's not a square or a rectangle? What if it has these kind of pointy shapes like we've been seeing? So what if it looks like a boomerang shape? Okay, so those are all, pretend those are all straight edges. I should have probably taken time to draw straight edges, right? Straight edges. Okay, so let's have these all be straight edges. That's why I asked you to use a straight edge when you're handing it off to your fellow classmate. It's hard to tell what's going on when they're not straight. Okay, so there's 4 vertices on each of these. The art gallery theorem says I need 4 divided by 3, at most 4 divided by 3. I don't need any more than that, which is 1.33, and again we can cross that off. So at most 1 guard. We can cross off the decimal part and just have 1, not 1.33, at most 1 guard. So let's look at these shapes and decide, does it matter where the guard stands? So the guard has to stand at a corner. Okay, always in this problem, the guard stands at a corner. Yes?
For the boomerang one, it does matter where he stands because he stands in the 2 points.
Good. Good. So for the boomerang one, the guard has to stand here or here to be able to see down into those 2 points. Good. Okay, so if the guard was down inside one of those points, the guard would not be able to see into the other point. So there, the guard would need to be at either of these 2 corners. How about this one? Does it matter? No, that one doesn't matter. Doesn't matter on the rectangle shape, but on the boomerang shape one, we have to pick correctly. So I just wrote pick correctly. You pick either this point or this point. Well, we could keep going and looking at 5 vertices, 6 vertices, and so on. But what we're going to do is look at the proof of the art gallery theorem and see why it matters from looking at the proof. I also wanted to look at this proof with you because it's an example of how mathematicians propose a theorem. So that's what one of the Klees did. I can't remember. I think it was Victor Klee. Somebody proposes a theorem. Someone else proves it. So in this case, a person named Chvátal proved it. But it was a very difficult, long proof. And so somebody else came along and made a beautiful, elegant proof. So we see the metamorphosis of the idea. This is from your textbook. Creative ideas can arise anytime and anywhere as long as our minds are open. The story of how Steve Fisk came up with the idea for his proof is a wonderful and funny real-life illustration of this maxim. Here Professor Fisk recounts the episode. This is Professor Fisk and his future wife Judy Lloyd at the time of the proof making. So here's the quick story. My wife and I were traveling across Asia during 1975 to 76, and during our 1-month stay in Iran, I visited the math library at the University of Tehran. That's what you do on vacation too, right? You visit math libraries? Yes. I read Cheval's article, or rather I looked at it. So his proof, do you know how to say this? Can you tell us how to say this properly? I don't.
Is that French?
Oh, I guess not. Okay, I don't know how to say that properly, but evidently his, do you know how?
I just said it, but Cheval, something like that.
Thank you. I'm not even going to try and repeat it. Evidently his proof was really difficult and quite long. So he looked at it, Professor Fisk looked at it, for the proof seemed so complex that I didn't want to read it. I did like the result though. A few weeks later, we were traveling on a bus between Herat and Kandahar in Afghanistan. It was a hot, dusty, and noisy, with squawking chickens on the roof. I was thinking about it, well, I was probably dozing off actually, and I thought of the proof. So let's take a look at that proof. It's so beautiful and elegant that it's included in a book on beautiful, elegant proofs. This copy is from Wikipedia that I have. So this is the art gallery problem posted on Wikipedia. And here's Steve Fisk's proof. We have here a polygonal closed curve to work with, okay? So we can follow it along in the proof. First, the polygon is triangulated. See, it's made into triangles. And you have to make the triangles by connecting vertices, only vertices. Don't make triangles like in the middle of the line segment, just connect vertices. And then, as you connect the vertices, don't cross your lines at all, okay? Because you have to triangulate it without adding extra vertices. It is known that the vertices of the resulting triangulation graph may be 3-colored. So I use 3 colors. I use green, blue, and yellow here. Clearly, under a 3 coloring, every triangle must have all 3 colors. The vertices with any 1 color form a valid guard set, because every triangle of the polygon is guarded by its vertices with that color. Since the 3 colors partition the end vertices of the polygon, the color with the fewest vertices defines a valid guard set with at most n divided by 3 guards. So like many proofs, once someone thinks of the idea, it's beautiful and elegant, and you're like, oh, of course. So let's understand better what he's doing, okay? So he's dividing any polygon into 3 into triangles because he realized, like we discussed, that any of the triangles can have a guard at any corner and see the entire triangle. Just like you had pointed out, a guard at any one of these corners can see any triangle. Also, he realized that you can color the vertices or the corners in such a way that all 3 colors show up on every single triangle. So once we pick a color, that color is going to be able to cover all the triangles it touches. So for example, pick yellow. If we look at the yellow dots, this yellow dot, a guard at this yellow dot can see into all 4 of these triangles because this yellow corner is on all 4 triangles. The guard at this yellow dot can see all 4 triangles that the corner is attached to. The guard at this yellow dot can see the whole triangle that it's attached to. So we can pick any color and do that. If we pick the yellow colors, then we only have to have 3 guards, 1, 2, 3, and they can see the entire area. You could do that with the green or the blue, but to pick the least, I picked yellow because that one only ended up having 3. And if you wanted to finesse this, at the end you could say, well, you don't really need this yellow guard because this yellow guard can see up into here. But don't do that on your quizzes, okay? You will need to be able to do this on a quiz. In fact, we're going to practice doing this now. We're going to take a polygonal closed curve, we're going to triangulate it carefully, and then color the corners and pick out a guard set using the art gallery theorem. Nicholas, would you mind passing these out, please? So you can download this from the Canvas homepage. Thank you.
I knew it was gonna be. It's like galaxies, but it's in the bathroom.
And we're going to write down what we need to do on these, okay? We need to triangulate. You need to triangulate carefully, okay? We want to only connect corners. Don't cross lines at all. That would introduce new vertices. And the theorem said don't do that at all. Don't introduce new vertices. Then we're going to color red, white. We'll use red, white, and blue. And we'll just write RWB. Then we'll be patriotic. But you don't have to have those colors on hand. Thank you. And then we're going to count the vertices and list how many are of each color. Once you've done that, you can find out the color that you use the least, and that's the number of cameras you need, or security guards. You do need to be careful when you're coloring the red, white, and blue. We want to make sure you have no duplicating, okay? You need to have a red, a white, and a blue on each triangle. Okay, you don't want to have one triangle with 2 blues or one triangle with 2 whites. You want to have 1 red, 1 white, and 1 blue on each triangle. There's more than one way to do these, but we'll work together on the first couple so that you can get the hang of it before we go on. Do use a straight edge. So use your ID if you don't have a ruler with you today. So when you see this, you'll see a figure like this on the quiz. Actually, you'll see a couple figures, and the quiz will say, ignore the shape that's not a polygonal closed curve. So you'll have to pick out which one's a polygonal closed curve on the quiz. And then the quiz will say, show your understanding of the art gallery theorem. By doing the instructions that I just numbered above there, okay? By triangulating and coloring. Okay, and placing the guards. So let's go ahead and start triangulating. You just connect 2 corners. Remember, you only connect corners. And if you've made a triangle, then you're done on that. If you're not sure that you made a triangle, then connect 2 more corners to make sure you have a triangle. If you're not sure your triangle that you created had a straight line, and you'll see what I mean sometimes. Probably on one of these other ones you'll see what I mean. So we just connect corners, and we make sure we connect corners without crossing any lines. So I'm not gonna connect there to there. Don't do that. Connect only corners. And don't connect in the middle of a line. So for example, don't connect to the middle of the line here. Only connect corner to corner. And if you're doing yours a little different than me, that's okay. Oh, here's a perfect example of what I meant. Here, if I connect these 2 corners It kind of looks like I made a triangle there, but I'm not sure that's perfectly straight. So I will connect again. If you're not sure it's a triangle, then connect 2 corners again, like that. Like this for sure is not a triangle, is it? But if you weren't sure, connect again. So I'm going to connect right here and make a real skinny triangle. So that's kind of an actually weird way to draw this. But I didn't cross any lines and I only connected corners, so it's okay. If you did yours a little different, it's okay. Only connect corner to corner, not to the middle of the line somewhere, and do not have any of your lines that you drew crossing. Well, once you've done that, you're ready to do red, white, and blue. So we all probably did this one on top, so let's start there. You put your red, white, and blue. I put the red on the top and the white and the blue. Again, it doesn't matter. There's more than one way to do this. But what is important now is that you keep with the next triangle has to be one you already did a side for. So we already did a side, the white and blue side of this triangle. So I have to do this triangle. I have to finish the triangle I have 2 sides with before I go on. Otherwise, I'll really get a mess later. So blue, white, this corner needs to be red. Then I have a side figured out, 2 corners of this triangle, red and blue. So I have to go to that triangle. So whatever you have done one complete side of, do the triangle that's attached to that side and get that 3rd corner. Otherwise your colors won't come out right. So I have red and white, I have to put blue here. Now I have red and blue, I have to put white here. Now I have red and white, I have to put blue here. So now I have 2 sides of 2 different triangles, 2 corners on 2 different triangles, so I can continue there. Blue, white, red, blue, red, white. So you should be able to do this so you have red, white, and blue only. Not a triangle with 2 blues, not a triangle with 2 whites. And I can help you with that, or Nicholas can help you with that if you got stuck. Okay, so let's count the vertices. How many vertices were there? I'm going to start up at the one right here and count. I always mark off the one I started, or else I count twice. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 vertices altogether. Now let's see how many we made red, how many we made white, how many we made blue. And yours, again, might be different than mine. For red, I did 1, 2, 3. For white, I did 1, 2, 3, 4, 5. For blue, I have 3. The last class I did, I had different. I had, yours might look more like this one. For my first class, I ended up having 4, 4, and 3. Did anybody else have 4, 4, and 3? Yeah, that's fine, right? Just as long as you don't have 2 whites on one triangle, or 2 blues on one triangle, or 2 reds on one triangle. Okay, well then pick the one that's the smallest if you only had 1, 3, or I have a choice between red or blue. I like blue, so I'm going to pick blue, and that's where I'm going to circle. That's where my security guards are going to go. And that's where they'll be able to see the whole interior of the art gallery. So this blue is on the corner of 3 triangles, so it can see all 3 triangles. This blue is on the corner of 2 triangles, so it can see all 2 triangles. This blue is on the corner of 4 triangles, so it can see all 4 triangles. Now when you're doing this, you might say, oh, but this blue can see everything this blue needs, and then you'll be tempted to cross off this blue. Don't do that, okay? Because what you're doing is you're showing your understanding of the art gallery theorem. So in real life, yeah, you can take out one of the security guards, but don't do that here. I need to know you understand the art gallery theorem. Well, this is as far as we got in my first class, so we'll be practicing some more of these until Wednesday. So please bring this paper back with you Wednesday, and we'll look at it some more. I'll see you then. If you weren't sure on how yours came out, make sure you see Nicholas or myself after class, please.